This is a production of Cornell University.
All right. Well, thank you for the opportunity, and hopefully you guys find this valuable. So the presentation's pretty simple. It's just a bunch of pictures, to be honest. I'm just going to ramble on. So feel free to ask questions, interrupt me, and basically I'm going to showcase some technology that we use, some current technology in agriculture, but all kind of focused around the precision world, and then talk a little bit more about our company and the vertical integration that we've employed and the sustainability of that. So kind of call this, the three kind of parts here: crop production, carbon conservation, and then the vertical integration. So we're going to talk a lot about precision because I think that's the focus here. So, this stemmed a lot from 4Rs. You guys all know what 4Rs are. So right source, rate, time, and place. So basically, I'm going to talk about how technology, what technology is implemented, what technology we have to accomplish these various things that kind of focus or are part of sustainable agriculture. So talking about right product, right source. Like I said, a bunch of pictures here. Top right is just a cover crop. So that's a heavy grass-based cover crop, as you can see. So cover crop is becoming a huge source of nutrients, grabbing waste nutrients from the prior crop and sourcing nutrients for your future crop. We'll show you some pictures later on that have polycultures. We do very little monoculture cover cropping. The polycultures is really where you start to add a lot of value. The picture on the right and the bottom left is something I've worked with Doug Young, Spruce Haven Farm. Probably a lot of you guys know Doug, have heard of him. Very active in research and sustainability in Cornell. So that's a boom that we've built and designed that actually applies manure to a standing crop. You can see it's applying manure in the bottom right here to maybe 2 foot tall corn, but we can go up to 6 or 7, 8 foot tall corn. Shows tremendous promise. So this is manure applied to a growing crop. We don't quite know why, but we grew some incredible corn. Here on the right is a test plot that we did that had the boom plus commercial fertilization. The boom, the dark green areas are where we had the boom applied manure, and the boom applied manure exceeded even heavy rates of commercial fertilization. The more interesting part, we did all three. We did this field. This is our home farm. This field, and that's Spruce Haven, sorry. So we did these 3 fields with the boom. We did these 2 fields holistically with the boom, and obviously this field had the trial in it. These 2 fields, we green seeded corn. That's actually planting there into a couple foot cover crop. It did not come up very well, did not have great stands. It actually got fairly dry. It was pretty ugly looking corn. We put about 30 pounds of nitrogen down, and we killed the cover crop after planting. Okay, there was a heavy cover though, killed after planting. We came in with the boom and did 2 applications on these 2 fields of about 2,000 to 3,000 gallons of manure applied in season. One at this stage and one, maybe 4 or 5 vegetative stages later. We took 300 bushel corn off of this. It was unreal, the yield for the input. So we don't, we have a bunch of ideas why, but just showing a, kind of an optimal source and some technology or lack of technology, but to get it applied. So moving into rate a little bit, you guys have all seen soil maps, variable rate stuff. It's just more showing you that something we do. We can do this very well. This is grid sample data. Grid sample data is kind of becoming archaic now. We have even higher resolution, lower cost, faster sort of sampling techniques now. But grid samples, core samples, spot location samples are always necessary to kind of correlate and calibrate. So getting good baseline data is an aspect. pulling soil data. You guys have seen this, normalizing maps, making useful maps that you can put into your equipment. It's kind of taking that data, running it through whatever filters, algorithms you see fit, and trying to generate maps. We do single product application for most of our applications, all variable width, all variable rate, section controlled, very precise. And we have been for quite a few years. So we're starting to get things balanced out. Things from poultry manure, eggshells, gypsum, lime, and then your NPK, sulfur, all of that stuff is all independently spread on prescriptions and spatially located, spatially applied. Oh, sorry, everything's a little John Deere based, a little biased. Every company has the same technology. It's going to look a little different. It may act a little different. We use primarily John Deere, so it's what I'm familiar with and what I can talk about the easiest and fastest. So, but like I said, and it doesn't matter about manufacturer. They all do something very similar. So this is a John Deere nozzle. It's called the exact rate, I think, nozzle. It's pretty cool. It uses two nozzles. Obviously, that's a filler, but it'll say it uses two opposing nozzles simultaneously. Okay, so what this allows us to do is spray at a desired droplet size across a wide range of speeds. So as we all know, drift and chemicals and all this becoming much more specific on what sort of particle size, what sort of pressure, what sort of nozzle, what sort of application height, all of these details are becoming very important. Get the right crop coverage, leaf coverage, penetration, whatever you may be trying to accomplish. So traditionally, you have a nozzle, it's got a hole in it, and you put a pressure to it, and obviously, depending on the pressure, you get a droplet size and a rate. And you drive your tractor across the field, and sometimes you could go up and down with pressure a little bit and get a little variance. But as you went up or down in pressure, your droplet size changed, right? Because you're putting more pressure to get more volume to go faster, but that shrinks, generally speaking, shrinks your droplet size. So this nozzle has fixed all of that. So what this does, as I said, it's got two nozzles that run simultaneously. We'll call one a small, low volume and one a larger, higher volume nozzle. And it's got solenoids. So I can start at a dead stop at the edge of my field and just start going nice and slow and speed up. And as I start off slow, the small nozzle starts pulsing. So it's got a little solenoid in there. It'll pulse 100 times a second or 1,000 times a second. I'm not exactly sure. Pretty fast, but it'll pulse. Sorry, I should back up. You basically tell the system what particle size you want. So say I want, a half a micron particle size, and that runs at 40 PSI. So I tell it that, and I tell it I want it to hold 40 PSI, so I have this ideal droplet size for the chemical I'm putting down in the right scenario. So this system will hold that at 40 PSI all the time, no matter what. And the way it adjusts the rate, and I say, okay, I want to put 10 gallons down an acre or 12 gallons down an acre. It will hit 12 gallons an acre and 40 PSI 100% of the time. The way it does that is when I'm starting going real slow, it takes the small nozzle and it pulses it, and it pulses it fairly slowly. Pressure's always 40, and it's pulsing it fast enough where it comes out as a consistent spray. But if you look at it under a time lapse or something, you'd see there's breaks in the spray, the application, but it's so fast doesn't affect coverage. As I speed up, those pulses get faster and faster and faster, right? And ultimately that slow or low nozzle becomes all on. At the point when that nozzle's all on, if I keep going faster, it actually shuts that one off and starts pulsing this one. So it starts pulsing that one, pulse, gets faster and faster and faster until that's all on. If I keep going faster beyond that, it starts pulsing both of them. It pulses both of them up till they're both all on, and then I can't go any faster. But I can spray somewhere between, like half a mile an hour and 16 miles an hour with these combination nozzles, and have my set desired flow rate of 12 gallons an acre and 40 psi. So it's pretty amazing what it can do. Additionally, the sprayer has individual nozzle control and curve compensation. So what that means, if we're doing point rows or something, it shuts off one nozzle at a time. My nozzles are 10 inches on center, so I got 10 inches of coverage. Every 10 inches, that sprayer turns on or off a nozzle. So it's very high resolution, so we don't get double application. We don't get skips. And then additionally, our sprayer is 120 feet wide. So if you're going around a turning like this, obviously the outside is going tremendously faster than the inside. And the inside at some points is actually going backwards. So what this does is it knows where each nozzle is and knows the actual, linear velocity of the nozzle and sets the rate. So each nozzle in a turn is actually putting down a different rate so that my application across the soil is consistent, even in a turn. Corn planters do the same thing now. So we'll talk a little bit about that in corn planters. So very cool nozzle, very kind of simple thing, simple idea. A lot of computers, a lot of knowledge. We also have see and spray now, so a little camera for each nozzle. It can, sense weeds and spray just the weeds. So there's tons of technology here. This is just an example of the right rate, I guess, is what this would be, and the consistent rate. So it makes things very effective. And as we develop biologicals and growth regulators and all of these, different herbicides, pesticides, insecticides, this is very important. We use this a lot. So continue with technology. I'm kind of a little scattered on this, kind of getting a whole bunch of things, but I think that's what I was asked to do, is just kind of show you guys some of the technology that's there. And I kind of cored it around this 4Rs idea. But so this is our planner. The reason I have this up is to show controlled traffic. So you'll see the tractors on track, the planters on tracks, and you'll see these dark lines here, or wider lines. This is 20-inch planter, 36-row 20-inch planter. These two rows right here and right here are both 26 inches wide. There are control traffic tram lines. So every piece of equipment that we run in the field runs on those two tracks. So the planter, the fertilizer spreader, the sprayer, the combine, the tillage tools, they all drive on those same two lines. So we don't know how many of you guys are, know this, but when you're going across the field, if you have a tractor and a wagon per se, like 90% of your compaction is put in with the front axle, because that front axle takes that nice loose soil, pushes it down, and then that rear axle comes across and pushes it down a little more, and then that front wagon axle comes and pushes a little bit more. But basically, eventually that ground gets really hard, and you're not putting down any more compaction. So for us, these strips are super compact, right? Can be good and bad. It holds up our sprayer when it's a little too wet because that ground's compact. Allows us to get out there maybe when we shouldn't. But it also just limits the root growth in those 4 rows, the 2 on either side of that. The rest of that field is basically untraveled on and uncompacted and virgin soil. So we get, detrimental production right there and there, but the rest of the field is in very good shape. So control traffic and tram lines. Yeah, so we put in our own RTK network. We were the first ones in New York, and we actually sell and allow people to buy subscriptions. We've had it 15 years probably. So we can repeat year after year within an inch of everywhere. So yeah, they've been 2009. We started with our tram lines, and so we have a bunch of guidance lines. There's like 2009 RTK, 60 foot. And those were still running on those same lines. So is that 15 years driving on the same spot? So I'll tell you, we have some muck soil. Doesn't work in the muck. We have big old ditches, so we have to shift it in some soils. It doesn't work in all scenarios, but in traditional upland, it works really well. So I think the next one's on the planter. So so we talked a little bit about herbicide or fertilizer application with the sprayer. So now we're talking a little bit about seed and in-furrow fertilization. So this is a new, again, John Deere, but this is what they call the exact merge, I think, planter. And basically, it drops a seed very precisely in a very consistent manner. So You've heard about fence row stands. You want all your seeds to be spaced at the same thing, because if you have two seeds too close, one overpowers the other one and it may skip an ear or something. So you want good soil utilization, good root growth areas, good solar capturing. So having a good stand provides a good yielding crop. So as these units go through the field, they hit a rock or something and they bounce and shake, and the seeds get shaken and fall off and bounce around in a seed tube, and they don't come out evenly. This eliminates all of that. So what up here, there's a seed disc and a vacuum that selects the seed, separates them, and drops one seed every, however fast you're going, however, whatever distance, every 6 inches, it'll drop a seed. Traditionally, there'd be a seed tube that would come down here and have a little bend at the back like this. A lot of people don't know that, but that seed tube had a bend that actually discharged the seed at negative 5.5 miles an hour. So backwards at 5.5 miles an hour. So if you were planting at 5.5 miles an hour, that was perfect, because that seed dead dropped. It came out with zero forward or back velocity, and it dropped right in the seed trench. But if you were planting at 6 or 3, it would either have positive forward or negative backwards velocity, and it could roll, and then your seed spacing would be off. It could also bounce around in that seed tube, get scraped, dented, scratched, as well as like hung up as it's bouncing. If the next one doesn't bounce, then it might catch up to it and you might get 2. So what this does is it has a brush system. So it comes in, grabs the seed, and actually physically carries it down and then discharges it. Cool thing, it's on electric motor and the speed changes. So curve compensation again, and go any speed I want now, and we don't have to, it's always a dead drop. So the speed of these bristles right here is identically match the speed of the tractor. So that seed is always coming out with 0 velocity and getting dropped straight down. So we have perfect seed placement now. Okay, so good start. In-furrow fertilizer. In a planter, we do, generally speaking, do 2 types of fertilizer. We do in-furrow. So obviously the double disc opens a furrow, drops a seed in, and then closes that. So you can actually put fertilizer in that furrow, and it's right where the seed needs it. Or you can do 2 by 2. So we go 2 inches to the side and 2 inches to the low. These are the general. Different farmers do different things. And you put down more fertilizer there and a little hotter fertilizer. If you put too hot or too much fertilizer on the seed, you'll burn the seed and it won't grow. So you're kind of limited, and it's very expensive stuff that you put in the furrow. So traditionally, we'd have a tube in the front here that would dribble fertilizer out, and you'd have basically a line of fertilizer down the seed trench here, which is great. It's right there. The seed, sprouts, comes out, the roots get the fertilizer right out of the gate, which is good. But as I said, it's very expensive fertilizer. We're now putting growth regulator, fungicides, insecticides. I mean, we can be putting down $10, $20 a gallon stuff in the trench here. And if we're doing 5 gallons an acre, that adds up very quickly. So we now have technology. Different companies call it different things, but Shshot basically. So we have a apparatus here with some electronics that will shoot a strip of fertilizer right under the seed. So last year, I applied 1.5 inch strip of fertilizer for every single seed, and nothing in between. So on 20-inch rows, my seeds are about 9 inches apart. So instead of putting down 9 inches of fertilizer for every 1 seed, I put down 1.5 inches of fertilizer for every 1 seed. I have choices then. I can continue to put down the 5 or 6 or 7 gallons an acre that I would have put in a 9-inch strip, or I could drop it down to 2. We dropped down to about 3 gallons. So we actually had a greater concentration, more fertilizer, more fungicides, more growth regulators, more insecticide, whatever, right where the seed was. Pretty cool that we can do that at these various paces. So really, really pretty innovative thing, and can save a lot and get the greatest return out of that investment in that fertilizer.
How expensive would this planter be?
The
What is it
planter?
Yeah.
With all the stuff I just talked about, it'd probably be $700,000 for a 24-row 30-inch. So they're not cheap.
No.
So last year, we actually just bought a new planter. This will be our first year on it. But last year, just general maintenance on our planter, we spend 40 grand in parts. Just, that's an annual cost to make this thing plant well. So like these discs right here, you see that's the double disc opener. They're about 35, 40 bucks a piece. We had 72 of them on our planter, and we throw them out every year. Because if they get too small, then they don't touch as much. You get a W in the bottom of your seed trench, and then your seed is rolling. So, you know, they're only worn about a quarter inch to maybe a quarter to maybe 3/8 of an inch. But at about half an inch to 5/8, they're shot. So we could truly, for us, we get about a year and a half out of them. So we end up throwing them out every year. So it's very expensive to run this thing and maintain it. So, some other things, this thing has hydraulic downforce, so it's got a hydraulic cylinder that's pushing down on it to push it down into the ground. There's gauge wheels here that right up here, there's a load sensor, so it can tell how much pressure, we call it margin, how much pressure is on those gauge wheels. So the margin is the difference between what you're pushing down and what's being held up. Obviously, it takes force to push something in the ground, and we can measure then what force is being applied in excess of what's being pushed in the ground. There's also accelerometers on each row. Each row's got its own computer, or a couple now, but it can measure the ride. So we can measure the margin, say, hey, we want to push down with 60 pounds of force, of extra force, and we want the ride to be this. And that really drives the speed of the tractor, so that you get good seed depth. Because that thing's bouncing all over, it doesn't matter what technology you have. If it's not in the ground, it doesn't matter. Closing wheels, they close the trench. There's pneumatic airbags on each one, so you get a good, again, constant pressure on your closing wheels no matter where you go. It's not like a spring that changes. Lots of cool technology in this. We have frame weight distribution. So you see planters are big and wide. If I go back a slide, you know, there's a pivot here in the wing so it can follow the train, right? And each row unit can go up and down. But there's a ton of weight in the middle here and not much weight here. So these row units out here will actually pick that whole thing up. So now we have big old cylinders that push out and can push down on the wing so that you can get even weight transfer across the whole planter, so you get even planting depth. It's all automated. So on this planter, we did seed, we did in-furrow, there was tanks up on the tractor, we did 2x2 nitrogen, and then we had 2 other products in the back that we could direct inject. So we talked about Pivot Bio. We were direct injecting our Pivot Bio on here, and then we could also direct inject like a growth regulator or something else that we wanted to add kind of on the go. So we could do different rates of nitrogen, this is our 2x2, different rates of our pop-up, different rates of Pivot Bio, and different rates of growth regulator, all at the same time with the same machine, as well as different rates of seed. Pretty impressive machine. So there's 2 videos now. This is just our sprayer running through the field. It's not very exciting. Just pointing out a couple things. The driver's not driving. It's auto steering. We're running on the control traffic tram lines. There's this sensor right here is a boom height sensor. So it is sensing how high the boom is off the ground. We have 7 of those across the sprayer. This is actually a carbon fiber boom. So it's flexible and super light. All the nozzles are on the back here. This has 4 direct inject systems on it so that we can mix and match whatever we want and change, turn on and off on the go across the field. So a fair bit of technology. And this is just kind of showing how smooth it is. The next slide or the next video is turn automation. So my driver is not even touching the steering wheel. He comes to the end of the field, the sprayer turns itself. You're going to see it turn into tram lines that are the headlands tram lines, and then you're going to see it turn out of it and down to the row by row tram lines. So completely automated. He's not doing a thing. So. He just came out of the rows, running down the headlands now. So you get turn into the next pass pretty promptly here. See how accurately and consistently it comes in there. You see those wheels juddering a little bit. He's off. So simple GPS, RTK, but it's pretty cool that we don't have to do that. And we can just hit that time and time and time over and over. We're very intensively managing our crops. So lots of passes is what that means. And if you're driving over different beans and running over the crop every time, you're destroying more, you're doing more damage than you are good. Okay, so again, just sticking on the trim lines, this is a fertilizer spreader. I built this. It's a John Deere frame, and I imported the spreader box from Germany. This thing is cool, very progressive in technology. So it's got scales on the spreader box, so it self-calibrates continually the application rate. But even cooler than that is the spread pattern. It also self-calibrates. So this has 16 radar sensors that go around the spread pattern, okay? And it measures the velocity of the particles flying out of the spreaders. It's also got a weather station on it, so it can tell wind and speed. So if you have a crosswind blowing this way, it'll throw the particles harder that way, softer that way, because the wind is going to carry them. So if you're going into the wind, it has to, and then it measures that and self-calibrates on it. It's got 128 sections. So it changes. So it's got the spinners, and the vanes on the spinners actually can move with little microelectronic motors, and it can change the drop point on the spinner. So it can adjust the spinner pattern and spread width all on the go. So this thing's doing a ton of math and getting us very high resolution application on just a simple spreader. It's kind of funny. I imported the first one of these, probably 10, 15 years ago, and I had one of the first ones with a radar on it. And we were using it right along, and one day somebody showed up and cut all the wires off of it. And they're like, you can't use that. It was jamming our military frequency, the radar. Well, because we had the only one in the US and nobody checked that. And they figured it out. We couldn't use it for a couple of years until they were able to update the frequency and the wavelength of whatever the radar is. But so that was a funny day for us. Example of a cover crop. So actually, I'm kind of thinking about product here, source. This is a polyculture. You see, there's probably 10 to 12 different species here. So this is applying nutrients, a vast array of nutrients as it decomposes and at different times. So it's really tailored to feed the crop. So we will tailor our cover crop mixes for whatever crop we're following and what crop we're going to. And when that crop we're going, so first scavenging nutrients that are left by the old crop, and then releasing or exuding nutrients necessary for the future crop at the right time in the growth stage. Lots of thought and kind of technology that goes into picking your species and how to use them. So we have, nutrients, organic nutrients. This is like a liquid application. This is dry application. Just kind of showing a little bit of technology, but also different sources. Planting, green seeding. So you see the same, cover crops, all sorts of species here. You see how tall it is. Plant a row unit. So this is, the closing wheels, the airbag for the closing wheels. Those are the gauge wheels, the little load sensors right there. The accelerometers up here. There's the hydraulic downforce. I'm just showing you kind of some of the things that I showed in the last picture. Switching gears just a little bit to tile. Tile is very important in these neck of the woods. So typical tile system is laterals feeding into a main, and then the main discharging into a stream. So what we've switched away from this, and we are actually discharging here with into a leach field. So in the next slide is of one of my fields. But we don't discharge right in the stream. We actually discharge into a pipe that runs along the bank here that's covered with vegetation. So the water runs off of the field. We get it off the field, but we basically discharge it into growing grassed waterways. Those plants, there's a lot of willow, absorb those extra nutrients, grow on them, and then basically filter the water before it gets into the waterway. So it's just very sustainable for our lakes and waterways. So here's a field that's grid tiled. So you can see the main here, main laterals coming up here and all the tiles. So these are every 20 to 30 feet. So we can really move water. And here's the field I mentioned. Here's the design. So we actually have field water coming across from a neighbor. So we piped it into one area, did a forested grassed waterway here, grassed waterway all the way down into, this is Vaness Brook. I think it's the third main tributary into Owasco Lake. And obviously Owasco's been the highlight of the blue-green algae and all of that. So we have the last agricultural property on one of the major tributaries to Owasco Lake. So that's where we've done a lot of this research. So this is a grass waterway that we built around Vaness Brook. And so this is also grid tiled like this. And it discharges here and then runs, all the discharge water runs along 2 leach lines that go up and down here, discharging all the water runoff from here into this grass waterway that then flows over. And although that's all seeded with, I think we put like 5,000 to 10,000 willow trees in there, and various grasses to capture the nutrients. So just a little different type of technology, not iron, but process. So transitioning a little bit into our business. I didn't really give the background or the history. I kind of got right into it. We started farming in Adirondacks, had some beef cattle. When I was 7, we moved to Cayuga County, switched to just crops. I came back after college and decided to make it a career. When I did that, I started a feed business, so making feed for the local dairies. And that business has grown over the years. So just kind of a little, we plant, we grow, we harvest, we process, we feed, and we fuel. So we are now making biodiesel as well out of the soybean oil from the soybeans that we grow. Last year, we planted all of our crops and ran our fleet of 30 trucks on biodiesel that we grew from the crops we made. So it was an awesome full circle scenario. So here's a picture of our farm. Well, you can see the planter there. There's another bin up now, but this is where I grew up here, and the farm ended about here. When I was born, this was the farm. It's grown a little bit. This is primarily the feed processing side of things at this point. So we make roasted soybeans, which was our first feed. We do cornmeal, non-GMO, GMO cornmeal. So we provide almost 100% of the non-GMO cornmeal that the local dairies feed and supply Fahe yogurt with. That all comes from us. And we got that contract. We bid that contract and the compliance with the dairies bidding that 7 years ago now. So we've been the sole supplier of the non-GMO cornmeal. And then this is a fairly new product. It's a mechanical extrusion plant. So we press or extrude and press soybeans. So it creates a bypass protein. It's very advantageous for dairy animals. And we then separate the oil. So we get about 3/4 of the oil out of the bean. So we have a low-fat, high-protein meal and a solvent-free, all-natural soybean oil. We also have, so that's what's going on here. This plant for soybeans, so let me back up. The roasters, we did a couple 100,000 bushels a year of roasted beans. Not a whole lot, 1,000 bushels a truckload. So we did 200 truckloads a year, roughly. Cornmeal, we're doing about 3 million bushels of cornmeal a year. Again, not a ton. The soybean plant for the extrusion, we have capacity. It's not there yet. We have capacity to go up to process 3/4 of the beans grown in New York State, which is pretty awesome. That'll be like 12 million bushels of beans, and almost all of the state's beans coming through this facility at some point. And all of that feed's going back to the New York dairies. We're working to get into poultry and swine. There's a fair bit of poultry. There's not too much swine in New York, but slightly different kind of operating parameters. And then the goal is to not only feed, consume all of the beans, feed the majority of the animals, but also bring and produce fuel and bring it back. So we have a biodiesel plant as well. This is something we've invented, created over the last few years. Super low energy, very carbon efficient, very simple, honestly. we can make 20 million gallons of biodiesel annually. The New York home heating market's a 50 million gallon market. So we have the capacity to play a significant role in that. But honestly, my goal is to not put it in homes, it's to put it in tractors and trucks and plant the crop on the oil and energy that we produce. So the whole circle becomes very, very efficient. So the bin, I didn't mention this. I mentioned that there was another bin here. That bin alone can hold 1/15 of New York's beans that we put up. It's the tallest bin east of the Mississippi. It's almost 1 million bushels. And like I said, it can hold 1/15 of New York's beans, and we fill it every fall. We fill it a couple times a year, actually. So that speaks to the efficiency. That's why I say that is we fill that bin out of the field. So those beans don't go to some farm, get elevated, dumped in a bin, pulled back out, loaded on a truck. They come from the combine to a truck to us. So it again just adds to efficiency and reduces the carbon footprint. So total, we have 2.2 million bushels at this facility of storage. So I think that's kind of the end of the pictures. So we got some time for questions. Yes. You want to do the microphone or?
But there are two microphones. So
Okay. Yeah, go ahead.
thanks for covering the presentation. Earlier you talked about alternatives to grid sampling. Can you talk about some of those?
Yeah. So there's a lot of options. So initially you had like a Varus tool probably 20 years ago that did EC and pH, and then they also had an optics sensor to try and do organic matter. That was invasive to the soil. We ran one, and we could never get the thing to run an entire day in New York. They had these little like sapphire lenses, and a rock would scrape them and break them, and the pH. So it worked. Didn't work in stones real well, but it got very high resolution data. The EC worked because it was just discs, so that electroconductivity, basically how much of anything can the soil hold. So that was very good with that. Now we've moved away to like NIR sensors, gamma sensors. To be honest, I have a phenomenal farm manager, and he loves agronomy, and he's much better than I. So I'm getting a little bit more into the business side. So I've lost a little touch with technology. But so I haven't run these other sensors. He has, but there's basically it's about 18-inch by 3 or 4 foot plate, and you don't actually run it on the ground. It's about 6 inches off the ground, and it uses I think it's NIR, but there are gamma and radioactive wave sensors as well. They can penetrate various depths into the soil and give you good soil analysis. I don't know exactly what parameters you can get from them, but it's a good non-invasive tool. So we're using those now and just getting started on that in terms of a holistic kind of scaling. So yeah, yes.
Have you said that? Okay.
Okay. Question. Thank you so much, Todd. I have 2 questions. Are you using weather data and met data on your farm together? And then I was really interested in the tile drainage. Are you thinking about if it were a really dry season or a short-term drought, could you capture the water and retain it somehow? Or
Okay. Or weather. Is this not working anymore? It's okay. We don't do a lot with weather. Right. Actually, that was the one I wanted. Yes. So we track the weather, and we've used satellite imagery and NDI imagery. We've done all of that. We do 4 nitrogen applications to spread our risk with weather. The last being a side dress application. Our latest thing, it's called a Argus, Argus. I'm not getting it quite right, but right here is a sensor on that machine. It's fairly new. I think last year was its first year that we ran it, and the first year it truly kind of hit the market, and at least a beta prototype version. It's got 2 cameras on it, super high resolution cameras, and we can write our own algorithms for it. But basically, it picks up the crop density and the crop thickness and the crop color, and automatically runs through an algorithm and varies the rate. So instead of, we did satellites, they're not as good actually. This is a lot better and it's much more responsive. So as he's going through the field and the crop is changing, the application is changing. So it's kind of summarizing the weather and saying, what does the crop actually need right now? And we're applying based on that live. How to write the algorithm? That's a good question. You know, that's a real challenge. So you have the data. The other cool thing with that is I could have somebody running it. I can be sitting in the office watching the video. So, and it saves all that film to a cloud. So you can scout that way. Like, you know, we can have an operator go spread a field, and we can have our scout basically sit behind the camera and look at the crop and scout it. So lots of different things you can do with that data that kind of summarizes how the weather has affected the crop and what kind of treatment you need to get on it. You can see disease coming in, you can see lodging, you can see all sorts of things. Tiling, so has a lot to do with topology, right? So like the field that I showed you, there are a few times in the year where we could backfeed that, but if we're backfeeding that, that means Vanessa Brook is really high, and we probably don't need to backfeed it because there's, you know, the ground's already saturated. We do also run a couple thousand acres of muck that is diked, and we pump, and we do backfeed that. So we can basically flip the pumps. We can pump the water out, or we can pump the water in, so we can flood irrigate that through the tile system. It's got an open ditch system and a tile system. So the ditches fill up, then the water runs up the tiles. So that one we do have the option to flood irrigate. Yes. Yeah, we'll never get it right. We'll never know what's right. We've done it all. We've done deep ripping, we've done inline ripping, we've done chisel plowing, we've done strip tilling. I actually built a couple strip tills. I had a 20-inch strip tiller that I built. We do minimal till, no till now. We have a variety of no-till tools or minimal till tools. So every year is going to be different. Every farm's going to be different. Every field's going to be different. Strip tilling is great if you're flat. We did it a couple years and abandoned it because when you strip till down, generally speaking, we plant across the fall line. So therefore the headlands go with the fall line. And when you strip till with the fall line, it basically consolidates the water from 30 inches or 20 inches into 3 inches, and it just washed every row. It actually made the erosion much worse than if you'd done full tillage and kept the water spread out over the whole mass of the crop. So it worked well going across the hill, but you know, the headlands are a big part. So from that, we did that one year, and then next year we're like, okay, we'll just no-till the headlands and strip till the core of the field. But the nutrient management and the strips and the warmth of the soil, the deviation between the core and the headlands was so great, having strip tilled and no-tilled it, that was not very good as well. So now we are primarily minimal to no-till. We have a couple tools, again, John Deere, but John Deere does a really good job, in my opinion, probably the best, of having the full circle integration. So from the tractor to the tillage tool, to the GPS, to the display, to the cloud, to the data transfer, to combine, all that stuff John Deere has, and they've done it well. They've kind of been the forerunner at that complete thing. So one of the things they have now is automated tillage tools. So we can actually write a script for our tillage tool at this point, based on soil structure, yields, soil type, pitch, terrain, location, whatever. We can write a predetermined script. It has 5 different things that we can adjust on the strip till or on the tillage tool, and or we can adjust them from the cab. So it can be as easy as we have like a light, medium, heavy setting. So if we have some dairies that apply manure for us when they drag line. They do a fairly good job, but wherever they cross or pull the hose or something, they always rut it up. So it can be as simple as we're going across the field on very light, very straight, very minimal till, and we come to the cross pattern and we hit like heavy, and that thing just kind of sinks in, and the disc change and the pressures change. It does pretty heavy tillage, levels out those ruts for 20 feet, hit the button, and it goes back to the lighter tillage. Or, like I said, we can write a script that changes the whole setup of the tool depending on soil density or soil type or particle size in the soil or whatever. So it gives a lot of variability to create a good seed bed with doing as little tillage as possible. Again, same statement as earlier. It's how do you write the algorithm to make it right? That's the challenge.
Yeah, we
So.
learn, then after that, be honest.
Yep.
Yeah, I wonder, based on your sense of these trends in technology and automation, what do you think will be the role of human beings on the farm in 20, 30, 40 years?
It's a good question. I don't think we'll be in the seat, which is good. We already don't have to be in the seat. It's more of a legality liability thing. AI will start to optimize, being able to capture data and figure it out is going to be important. Until we can accurately predict the weather, it's still going to rely on a human to say, hey, I think it's going to be drier, I think it's going to be wetter, but if we can get weather forecasts and weather models that can accurately predict the weather, then it can just become math to figure out how to feed your crop and how to manage your crop. So obviously, if I knew it was going to be dry or if I knew it was going to be wet, I would make dramatically different decisions on what I do and how I treat my crop. So nitrogen, simply, I said we do 4 nitrogen applications. And if it's bone dry, our 4th nitrogen application, which is our most important one, can be completely ineffective. So you're taking risk by not putting nitrogen down up front if it comes off dry. You're taking a lot of risk putting down nitrogen up front if it comes off wet. So, like if I knew it was going to be dry, I'd put it all down up front. If I knew it was going to be wet, I wouldn't put any down up front or much less down up front. So it's how can we predict the information? But automation's coming, in terms of actually time in the seat. Yes.
Be honest, then that.
Yep, the boom.
That's something you could speculate. Am I speculating what the reason is why to have such? But I think I've had some conversations about it.
Yeah, so well, there's a part of it that's just irrigation, just water. It was reasonably dry that year, but I think it had to do 2 things: surface applied manure, so ideally, or generally speaking, not great, but applying it under the canopy. We believe, I think it's called nitrogenous. You guys probably know more than I. That there was some bacteria that ammonia comes up, and the leaves were actually able to capture some of the nitrogen that was volatating. Obviously, some of it went down. It was applied to the growing crop, but I think it was a stimulation of that bacteria and pulling nitrogen out of the air. If you looked at the pounds of nitrogen needed to grow the volume of crop that we grew versus the amount applied, there was a dramatic difference. So the question was, where did it come from? And we hope that it came out of the air. Obviously, some of it also came out of the soil, the residual in the soil, but the numbers that we were looking at indicated that we had to have been capturing some nitrogen from the air. And that had to do with some biological activity on the surface and under the plant canopy. I'm not the scientist though, so that's the farmer version. Yeah. I mean, we don't ever throw away data. We have data back from 2006, precision data. So it's not quite as precise back then as it is now, but we have it all. Yes.
2 last questions, so Richard and Tony, and then after that. What would be your wish list for your family at today's moment?
I think simply that tool right there, we don't own that. I think that tool would be a nice thing. As I mentioned, side dressing, this is how we side dress. That's wheat, not corn, but we side dress with a dry spreader. We could do it with our sprayer with UAN as well. But I think being able to actually inject UAN subterranean close to the row, I would not run these down the center of the row. I'd run them like 4 inches off the row, so shifted. But we have the ability to, we can steer that thing at this point. So we have the ability to really tightly control it. So I think expanding our ability to accurately apply nitrogen in season. So if it's dry, this doesn't work very well. This would work in a dry year. So that's probably a immediate kind of return need. It's simple. It's not super advanced, not super technological, but I think it'd pay some dividends for us. So our new planter switched to 30-inch rows. So this will be our first year on 30-inch rows in probably 10 to 12 years. So we have more ability to manage our crop at a higher resolution. The narrow rows are tough to get, especially side hills and small fields. In Midwest or where it's perfectly flat or on the muck, we can do anything we want in a 20-inch row. But you start picking a little side slope and you just start wiping out rows when they're that narrow. So it's really hard to manage intensely on a very narrow row system.
Next question from Billy.
Yeah, I mean, it's kind of looking at the future, and given that we have a lot of graduate students here today, I wanted your perspective. What kind of advice would you have for students in crop soil science, information science, very broad? What would be, kind of from your experience, something, boy, think of this as you're moving through your careers related to that?
Yeah, it's got to be implementable. You know, you guys, I've had many interns come from Cornell. You guys have phenomenal educations, phenomenal teachers, phenomenal like theoretical ideas, which is great, and we need those. Got to figure out how to implement them on the farm every day, how to make decisions at the farm level, on the raster level, on a very granular level now. So so I told you, our sprayer shuts off at 10 inches. Our planter's 30 inches now. The last one was 20 inches. So I want to know what I need to do on this 20-inch square of soil, not this 1 acre block. I want to know on 20 inches. I want to know what seed and what population to put on that 20 inches. So you guys have the theoretical background to do that, but you got to make sure it's implementable and expandable and consumable for the farmer, because the general farmer doesn't have the training and the background that you guys have. So how to make it consumable.
It's crazy how like 30 years ago, agronomists were kind of had the idea of precision ag, wanted like engineering, and today like engineering is way ahead of agronomy.
Yes.
Yeah. We need to catch up now.
Yep, for sure.
Yeah. All right. Thank you very much.
Thank you very much.
This has been a production of Cornell University, on the web at cornell.edu.